for having me tonight. Welcome to Data Science After Dark. Tonight I'll be talking about attacking a machine learning model and why it's so important to protect your proprietary models, or at least be aware of these type of attacks so that you're not blindly trusting the output from the models. My name is Jason Klein. I work with Logic Forte. I've been managing information since about 2002. My background is quite a mix of IT, software, InfoSec, and through the InfoSec side of things, I stumbled across this particular attack, but just working with data and having that combination of IT and software background has led to my interest in machine learning. Like I said, we work with a lot of data, and we're always looking for new and interesting ways to make that data work for our customers. The topic tonight, again, we're talking about attacking a machine learning model, specifically giving examples as to how you would attack a machine learning model, or how simple that process is, so that you understand why it's so important to protect any models that you have, or like I said before, at least sanitize any outputs that you get from the models. And examples of this, I mean, we're going to talk about image classification tonight, but this could think of any type of model that takes an input and generates an output. So from a banking perspective, that could be your mobile banking app. When you go and scan a check, and if any of you ever see checks anymore, and send that off to your bank, that mobile app is reading the handwriting on the check, if it's a handwritten check, and basically converting those digits to numbers on the fly, and telling you, okay, this is a check for $60, please confirm, and then it gets deposited into your account. Now, in that particular example, the model lives on the mobile device, so it isn't protected, it isn't private, and because of that, the bank knows that they can't trust that model 100%. Those particular models are over 99% accurate, but if somebody is able to trick the model into thinking that the check says $6,000 instead of $60, the bank would be on the hook for a few bucks. So behind the scenes, they're using it as a convenience for themselves and the customer, but behind the scenes, they have someone reviewing and approving every single mobile deposit. At least that's how it works at the bank that we're with. You see the same type of models for fraud detection. So let's say you're managing an e-commerce store or some sort of online platform where people are signing up for accounts. You wouldn't want that model to get out in the wild, because someone could learn how to tweak the inputs and maybe add specific items to their order, or change their destination address in a certain way to where it always passes that fraud check. Profanity and image filtering, same type of idea. Tonight we're going to talk about image classification models, and specifically we'll dive into the MobileNet model. It's a pre-existing model. It's something that you can download. You can easily run a Python script that downloads that model and reads an image on your computer and classifies the image. And so I'll show an example of that during the demo, where we have images of a dog or a frog or things like that, and it'll classify it and say, I'm 99% sure this is a dog, or I'm 99% sure this is a frog. But then where we get into trouble is, I'm going to show you another image that bit for bit is identical to the dog image, nearly identical to the dog image, visually is identical to the dog image, but all of a sudden when we run the prediction, MobileNet thinks that it's 99% sure that the dog is a frog. And so that's just an example of how things like this can go awry. I mean, we can train that model in seconds and generate an image of a dog that passes as a frog. It's not something that takes hours. I mean, I'm running this on a 4-year-old MacBook, and the fact that you can do this so quickly is reason for concern. All right, so before we deep dive into the demo, I want to give you a little bit of a history of machine learning, like how we've gotten to where we're at, and then we'll talk a little bit about a little bit more about image classification and how that has progressed over time. I mean, with machine learning, a lot of folks point to 1950 as the beginning where the Turing test was born. The idea being that that concept would be performed on a person and on a computer, and you wouldn't be able to distinguish between the two. You wouldn't know if the person answering the questions or if the computer answering the questions was a person or not. So that's really where machine learning was has its roots. When people started thinking like that, then they started looking into using machines, or now computers, to become more intelligent and be able to classify things and answer questions in such a way that it was indistinguishable from our own skill set. In 1958, the first neural network was born. In 1967, the nearest neighbor algorithm was born. So if you've ever taken computer science courses and they've talked about the traveling salesman, that particular algorithm is a way of trying to decide how I can best travel through a given set of paths or roads or nodes to get from point A to point B in the most efficient way. I mean, those kind of concepts are integral to things like Google Maps or any other mapping system nowadays. Fast forward another 10 years, sort of your first autonomous vehicle, the Stanford University cart, is able to navigate obstacles on its own. Another 10 years or so, machine learning takes a different direction. Up until then, when they'd been building computer programs that could play chess or play checkers or anything along those lines, they were considered knowledge-based programs. So they took what somebody knew and they put it into code. And in the 90s, they shifted to more of a statistical and probability model where, rather than writing down rules and building some sort of program that follows those rules, you were feeding data to the computer and letting the computer learn from that data. So, I mean, you fast forward to Watson beating Jeopardy or beating other contestants at Jeopardy, or more recently, computer beating other folks at Go. Those could have never happened through knowledge-based programs because we don't have the capacity to teach the computer and program all of the different rules and things that we know. But so instead, with the Jeopardy model, IBM fed tons and tons of online data to Watson. With the Go model, the folks basically had the computer continue to play against itself until it started to realize, I can do this or I can do that and be better off, and look from a probability point of view and say, this move is better than these other moves. So that was a pretty big shift in how we got to where we're at today with machine learning. Only 2006, which when you start to look at some of these benchmarks and milestones, it isn't really that far back, but that's when the term deep learning was coined, so 14 years ago. And then 10 years ago, we start to see a lot of activity. Microsoft Connect, a lot of you who may have used Xboxes or played any of their active games where you stand in front of the Xbox and it can see what the motion of your body. That device was launched in 2010 and was able to track 20 human features at 30 frames a second in real time, which was pretty groundbreaking at the time. At that same year, ImageNet was born. It was designed to be a collection of standard images that computers could basically use to or that data scientists could use to determine if their model is doing better or worse than the other known image classification models. So at that point, we were getting to where data scientists and other programmers were trying to take more advantage of deep learning technology and to teach computers things, and we were realizing that we needed a standard so that everyone could have some benchmark to compare their own efforts and their own progress. Google Brain, which drives a lot of Google AI, was founded in 2011. For everybody that loves cats on the internet, you might be excited to know that 2012 was the year that one of the Google labs developed what I called it, basically the YouTube cat finder, but it was a model that was able to scan through YouTube videos and fairly successfully identify videos that had cats, which in of itself may not sound super useful, but the idea being that they were able to scan through videos and find information was pretty groundbreaking 8 years ago. Deepface came out a few years after that, and that sort of brings us to where we are today. I mean, more and more things have happened since then, but you can see even in the last line, just in the last decade, more and more things are happening in the machine learning space. And if you think about everything that we use day to day, whether that be if you use Google Mail and it's automatically suggesting whole sentences for your email or any similar product, or if you're using Siri, probably a bad example. She doesn't seem quite as smart as Alexa or Google Home, but those things are all driven by this type of technology. Now, I'm going to move on and cover some history specific to image classification so that you can appreciate a little bit more about how these image classification models work, since that's what we're focusing on tonight. But each segment of machine learning has a similar story where you see that somebody somewhere had an idea, but everyone's ideas tend to build on prior work and we eventually get to the point where we are today. So with image classification, all the way back in 1959, sort of predating a lot of machine learning work, there's a groundbreaking discovery, or at least most people in the computer vision or image classification world would tend to say, by a pair of scientists named Hubble and Weissel, who discovered that when we're looking at things, or when animals are looking at things, they're not looking at the entire object. There tends to be a hierarchy of how you identify things. So the real key piece to their discovery was that cat was able to identify things primarily based on the edge detection. And if you fast forward to where we are, essentially 60 years later, with machine learning and image classification, pretty much everything that is being done right now, the image models start with edge detection. They basically tried to replicate how our brains work or animal brains work, and so knowing that this is the beginning of how you or I or an animal even would detect an image and say that's a ball versus that's a car versus that's a phone, was pretty groundbreaking. But that same year, another technology was developed, the first digital image scanner by Russell Kirch, and you can see a little picture in the background of his baby at the time. And even though it was fairly bad quality for today's standards, the idea that you could store an image digitally was born and allowed more and more progression in this field. A few years later, another person, Lawrence Roberts, was able to convert photos into line drawings. So building upon Kirsch's work and scanning photos, they were able to start building tools that could generate those edges that are going to end up being critical to the edge detection that we use in image classification. Fast forward another decade, the first neural network was born, and then I apologize. I know I mentioned the folks in 1959 discovering edge detection. They weren't the ones that discovered the vision hierarchy. That was a gentleman in 1982 who discovered that you start with an input image, you discover the edges, and then you start to understand objects based on those edges. And so there's a little bit of a graphic that demonstrates how they might do that with a computer. Fast forward almost another decade to 1989. LeNet 5 was the first modern convolutional network, which led to a very well-known image set called MINST. If you ever follow any TensorFlow tutorials or other machine learning tutorials related to images in the last few years, you'd often see an example that would have a ton of handwritten digits, so 0 through 9, and that set of images there, and there are literally thousands and thousands of these handwritten numbers. That was called the MINST image set, and so that dates back almost 30 years now that image set has been around. But 20 years ago, a pair of scientists created the first real-time face detection network, and I have links in all of these, so if you are super interested in the deep dive version of this, be sure to click on any of these footnotes to go out and learn more about each of these milestones. But in this particular case, they were able to find a super efficient way to feed images into the computer and run through some very simple layers where, regardless of the orientation of the image, whether it was up and down or sideways or upside down, they would run the image through these different layers where the very first layer would basically look for what's known to be sort of the darker area of your eyes compared to your cheeks, and if the image passed through that filter, then it would go on to the next filter, but it would run the image through that filter at different orientations, and it would just check different parts of the image. And because it was able to do these super simple checks so quickly, it could do that scan over a whole image, and if it found anything that passed that filter, then it would go on to another filter that would be more likely to confirm, yes, those are definitely eyes. And so it would run that same area through the next filter, and then if that passed, then there were several other filters where it'd probably check for nose and mouth and things like that. But the first known commercial use of this was in 2006, which seems pretty crazy to me that only 14 years ago cameras had real-time face detection. I mean, we take that for granted now, where you can hold your phone or a camera up to a face and it'll autofocus on the face, but they implemented this real-time face detection network in Fuji cameras back then, and I'm sure a lot of the other cameras had similar technology around then. 10 years ago, the ImageNet project was born. For those of you who haven't worked with image classification, you might have never heard of this, but it's pretty common in the image classification space. Basically, folks set out to, I mentioned this earlier in the more broad timeline, but I'm going to dig into it a little bit more. Folks set out to build, much like the MINST data set with handwritten digits, a standard data set of many, many, many different images. So whereas the handwritten digits were 0 through 9, meaning you basically had 10 classes of images. It could either be a 0 or a 1 or a 2 all the way through 10. I'm sorry, 9, so 10 digits in all. ImageNet had thousands and thousands of categories and ended up with over 14 million images. When it comes to building models, you'll find that you have to feed a lot of data into the computer to help it build this model. And so back with the MINST data set, they were feeding thousands of digit photos. And so you had hundreds or more of a 1 and hundreds or thousands of 2s and hundreds or thousands of 3s. And it was able to find patterns with those. So when you expand to ImageNet, they were doing the same type of thing where instead of having a ton of 1s and a ton of 2s and a ton of 3s, they ended up having a ton of dogs and a ton of cats and a ton of cars and different categories of objects that could be run through the computer and used to train models. But much like the MINST data set, where they needed some sort of standard benchmark so that people could see how well their model was able to identify numbers, the ImageNet data set allows people who are working with machine learning models and training models to compare their model or their end result with other scientists and other machine learning folks who are basically trying to help advance the field. And so, like I said, they're up to thousands of categories and tens of millions of images that have all been categorized and tagged, which is super time consuming, but that's really the only way to get the data we need to train these models. And at the same time in 2010, they began an annual contest that had a trimmed down set of their data, 1,000 image categories with many images per category that people would use to basically test out their models during the competition and show how their model performed to other teams. And so you see a lot of progress in the last decade. I mean, ImageNet started 10 years ago. 8 years ago, Alex from I don't know how to say his last name. So AlexNet won ImageNet. The story at the time was that prior to 2012, models were only able to predict images in that 1,000 category image pool at a reliability rate of about 75%. So there were about 25% errors. And AlexNet improved that quite a bit to where there were only about 15% error rate. And so you see, if you start to look back at the image classification tooling and progress, a lot of that stems from this AlexNet. That particular model was used quite a bit and spurred quite a bit of interest 8 years ago. Microsoft had a team that won ImageNet 3 years later or 5 years ago, and their particular model had 95% accuracy, which in of itself is already obviously an improvement over AlexNet, but is also a huge win because they estimate that humans are able to gauge accuracy of images within 94 point some %. So at this point, this was the first time where an image classification model was considered potentially more accurate than most humans. And now 3 years ago, one of the last competitions, ImageNet announced that a majority of their teams were able to produce models with 95% accuracy. At that point, it's more of a matter of making more efficient models than more accurate models. A couple things are happening in this space. They've learned, or people have pointed out, that all of these images that are tagged and categorized and ready for people to use to build models that you and I benefit from when we have a photo gallery and we say, show me pictures of skylines or sunsets or things like that. The work that's happening now continues to make those models better and better, but they found that the underlying data is fairly biased. There are some minor issues with it where, well, I'll throw out some links in the Slack, but basically you'll get consistent miscategorizations that tend to be either sexist or prejudiced or racist or anything along those lines, and they are trying to figure out what they need to add to the data set to eliminate that, because they certainly don't want people using models and ending up with results that could cause folks problems. Another big area of development with ImageNet is that they're basically moving on from 2D images to 3D images. So essentially 3D models that they would use to help predict or generate predictions in AR and VR applications. So folks that are familiar with virtual reality, augmented reality will start to see some benefits from this in the next few years. Now I'm going to cover very briefly how image classification works, but before I do, are there any questions? I apologize, somehow I've lost the participant list. Oh, here we go. You're welcome to raise your hand or just speak up if you do have anything. Otherwise, I'll keep trucking along and we'll have plenty of time for Q&A at the end too. So my goal tonight is really to give you a background of where machine learning's come from, where image classifications have come from, and then give you a high-level explanation of how image classification works and how this demo works. I'm glad to deep dive with individuals afterwards or send you links if this is a subject matter you're super interested in. But I realize that a lot of folks aren't necessarily working in this field or planning to do a lot with image classification. And so my hope is that your takeaway from tonight is how we got to where we're at and how it works in general. So first and foremost, when you're talking about image classification, the very first thing that you need to do is train a neural network, train your model, whether that be the model that AlexNet produced or the model that Microsoft produced 5 years ago, or the many different models that are coming out now that are based on their work. All of these models are essentially a neural network that have been fed images and then output a model file that then you can feed future images into, and they'll generate a prediction. So in terms of training that neural network, you basically end up with a ton of tagged images. That's where a database like ImageNet comes into play. You can't just feed the thing a bunch of images and have it deduce patterns on its own. At least we're not to that point yet. We're getting there. You have to basically feed it an image that also has some sort of tagging system, whether it be in the file name or a separate database that has a list of file names and then the metadata or the tag that goes along with them. Up until now, using ImageNet as an example, most of their photos are going to have a single subject. So you're not going to have a photo that has a burger and fries. You would have a photo that has a burger, and then you'd have a separate photo that has fries. And the benefit of that is then when they're feeding in the tagged images, they'll be able to feed the model an image and say, this image has a burger in it. And they don't have to feed it an array. Otherwise, think about if you're feeding an image with a scene, maybe it's sunset on a beach. Would you feed it, there's a sunset and there are waves and there's water and there's a beach? I mean, somehow you would have to distinguish between each of those items. And they're getting to that point now where you have tags that are smart enough to say this boxed area has water and this boxed area has sand and this boxed area has a sunset. And so it is certainly possible, but 10 years ago when they were first building ImageNet, that was something that was only going to happen in the long future. So again, going back to training your neural network, the gist of it is you input tagged images. The more the merrier. I mean, when they're training these neural networks, you generally have thousands of images, at least hundreds, but usually thousands of images per category. So if you're feeding images of dogs, for example, you might have additional metadata that says that this is a German Shepherd versus this is a Pit Bull versus this is a Boxer versus this is a Golden Retriever. And it is able to learn from that. And so you'll find that the models that we've basically ended up with from the ImageNet project will tell you, I'm fairly sure this is this kind of dog. So it doesn't even stop at dog. But the idea is they keep it simple by having a single subject in there. And so it's going to know it's a dog, and it's probably going to know what kind of dog. But you run that through, and behind the scenes, the neural network will train these hidden layers and end up outputting what some people call neurons. But if you look at a model for, say, the digit recognition, in that case, you would end up having 10 outputs. With newer models where you have potentially thousands of outputs, it's a little bit more sophisticated. But once you've trained that network and you go to use the neural network, that's pretty simple. You input that model file, you input your image, and it outputs a prediction. And I'll demonstrate that as part of the demo. So if I forget to do that, be sure to remind me. And then finally, profit. So all joking aside, though, if you've trained your own model, let's say it's something that's critical to your business and not something that you plan to open source or publish for the public to use, you really need to keep your model secret to help avoid the type of attacks we're going to be talking about. Now, I gave the example of banks using the digit recognition model on cell phones. I mean, if you're deploying something through a web browser or through a mobile device, it may not be possible to keep that model secret. But in that particular case, if you're if you know that your model has to be distributed to the public, you want to sanitize whatever output comes back from the model. So with the remote check model, I gave the example of someone fooling the model into thinking they were depositing $6,000 instead of $60. You'd need somebody to basically review all of those and just do a quick sanity check to make sure, yes, that says 6,000, and if it doesn't, then they can kick it back to the customer or make a correction. And for any of you who have done work in the web space, building websites and such, an example that might help you picture how this would look when you start working with some sort of machine learning model in the web space or the mobile space would be no different than, let's say you have a customer facing website, they log in, they have a drop down that maybe they choose which one of their locations they want to look at. And they click a location in the drop down and they click go, and the next page shows all kinds of private information about that location. When you're building a website, you would want to make sure that you're checking whatever location they're asking for on the back end. And so if they ask for a location in, maybe they're a customer in Springfield, but they want to see details for a location in Nixa, and they don't have access to that, they could go in behind the scenes and they could submit a web form that says, show me Nixa, and you need to be sure behind the scenes that you're doing a double check to make sure that they actually have access to see that location. And so I guess what I'm saying is with a model, if they're somehow fooling the model into producing a different output than you'd expect, just like they're fooling the web form into showing a different location than you'd expect, you just need to have some way of double checking or sanitizing the output. But the best bet is to keep your model secret or private, and perhaps you would have them send a web request to a server that hosts the model, and then the server returns an answer of some sort, rather than deploying the model to the web or to a mobile device. I know security through obscurity isn't the best bet, but it's depending on your situation and your model, you might be it might be appropriate. Skipping the boilerplate slide I accidentally left in there. All right, so we're getting ready to dive into the demo. And I've already mentioned this, that we're going to demonstrate how to easily attack an image classification model and how quick the process is. I'll also feed an image of a dog into the model, and then I'll show you how we can very quickly update the image in such a way that if a computer is comparing the two images, it would be hard pressed to know that there's any difference. If you and I are looking at the images, we would not see a difference, but for whatever reason, the model thinks that it's a completely different animal. And with that, I'm going to jump over to the demo. I'm going to talk a little bit about it first, but now we're getting into the fun stuff. So this particular demo is called Dog or Frog, and basically that's because when I first learned about this type of attack, I was participating in a cybersecurity capture the flag tournament called Pico CTF. It's more of an independent thing, so it wasn't a live contest, but the point is anybody could go out to Pico CTF and perform these sort of security puzzles and tests, and the 2018 competition had the following problem, basically saying, could you use one of those ENNs to help me out? I'd like a photo of me as a tree frog and have the neural network recognize me as such, but still have the photo look like me. And so this is a picture of the dog that they had in the competition, named Trixie, and they wanted you to feed the dog into their website, upload the image to their website, and convince their website that it was a frog. But the catch was they didn't want the image to be significantly different from the original image they provided. So you couldn't just upload a picture of a frog, because it would know that that was definitely not the same image. You couldn't embed an image of a frog over the dog, even if it was some sort of line or outline, because it was too far removed. It was too different from the dog image. And so I really scratched my head at that one, because I knew that there were different ways that you could go in and mess with images to embed hidden data in them, but I'd never heard of this approach where you would basically use the model from the neural network to generate a new image based on the original one. And so they go into a little bit more detail, pointing out that we're trying to build an adversarial example using the photo of Trixie, their dog, as a starting point, and that they were explaining that the website would use Keras and the mobile network to analyze the image, and the image needed to be classified as a tree frog at 95% confidence and be similar to the original image. And there are tools you can use to run this comparison, but their website was kind enough to tell me that to output these stats. And I'll pull up that website and show you what it looks like. It was pretty clever how they put this together, but they wanted to point out that this attack or this vulnerability can be applied to pretty much any machine learning model, and it wasn't specific to MobileNet, which is a very, very slimmed down version of ImageNet. They just went with this for the sake of everyone's sanity, because it uses less memory and requires less horsepower to generate a solution. They went on into a little bit more detail, basically explaining that what I'd already said, you're not trying to embed a frog picture in the dog. It's a little bit more interesting solution than that. They gave an example image that looked just like Trixie, the dog, but if you ran it through the prediction tool, it would tell you that it was a sea lion. And so let me, let's see, I'm going to dive into some of these examples and show you what this looks like. But if you want to deep dive into more information about this, or you are very interested in this space, definitely check out this Google article. It talks more about it. Just to show you what type of output they had if I uploaded a picture of a frog, rather than showing the dog, it would say tree frog, and it'd say, it's a photo of a frog, yes. So I was getting closer at that point. It was 52% sure it was a frog, which failed the test because it needed to be 95% sure. But the major issue here was that the hash distance between the original photo and the tree frog was rated this 13 value, which was far above where I needed to be. But you can see it thought it was either a tree frog or a tailed frog, but obviously it isn't going to say dog because it was literally a picture of a frog. So let's see here. I'm going to go into live demo. I copied some output here, but let me share a different screen. Any questions while I'm switching screens here? All right, no worries. Okay, so I'm going to share the original. Sorry, unshare, reshare. The original problem here, so you can see what I was seeing during the competition. All right, dog or frog. So when you're doing a competition like this, they give you some advice, some tips. In this particular case, they were a lot more forgiving. They linked to some notes, and they gave you a template to get started. And I'll show all that here in a minute. But basically, the way to solve a problem like this is you choose a file, and so let's see here, dog or frog. So if I take the original dog and upload the original dog file, it'll analyze it and it'll show me some output. Give it a second. And in this case, it even knows the dog type. But is it a frog? No. It's 51% sure it's that particular dog, 48% sure it's another type of dog, and then so on and so forth. So if you haven't seen prediction outputs like this, we're basically looking, assuming you can see my highlighting, we're basically looking at the tag name and then a percentage of confidence. So it's 0.51 or 51% confident that it's that type of dog, or it's 0.48% confident that it's this type of dog, a German Shepherd. So if we go back and we upload a picture of a frog, you'll see the output that I had just showed you. All right, and so now it knows it's a frog. Again, 52% sure that it's either a tree frog or 45% sure it's a tailed frog. But we have this distance issue. Let me share a different screen here. I think it's this one. All right, hopefully you can see my little finder here. I might need to share my whole desktop. I'm just afraid the resolution is going to make your computers explode. Let me try to share a screen so you can see what I'm doing here. All right, hopefully you can see this okay. If there's a problem viewing the screen, please speak up. You should be able to see, if you're seeing what I'm hoping you're seeing, you'll see a couple of Finder windows and a browser in the background. Can you raise your hands or say yes if you're seeing the right thing before I keep going?
Yes.
Yes, we're
Okay,
good.
good deal. Just making sure, just making sure. All right, thank you. So when we're uploading these images, you can see the original image of Trixie the dog, but then they also provided a sample image. And now, granted, this image is going to be skewed because it's been run through the neural network, and they reshape these images before they analyze them. But the point being, if you compare these two images, the image of Trixie the dog and the image of Trixie the sea lion, from your perspective and my perspective, there's nothing unusual about it other than it being scaled. And so I'm going to drag this down here, and I'm going to upload that sea lion picture. And even though it's a picture of the dog, the very strange thing here is, okay, it shows it's a sea lion. It's 99.9% sure it's a sea lion. And you can look at the other predictions. I mean, it's so sure it's a sea lion that this is like 1/100 of a percent confidence. The rest of these are worthless predictions. And so then that got me to scratching my head. It has a distance from the original dog photo of 0, which, I mean, visually makes sense, but I got to scratch my head, like, how did they do this? How would you take a photo of a dog and make make an image that looks like the dog, and as far as the computer is concerned, is nearly identical to the dog photo, but is classified as a completely different category? And I mean, well, I'll pull up the code here in a second, but you can see, I already did the frog. I thought I had some other images here, but maybe not. But they give you a starting point, and I'm going to switch over to my code. Let me zoom in here. Hopefully this is legible. Uh-oh. Okay, if I need to make that any larger for anyone, let me know. But this is my working folder. So they provided me with a copy of the MobileNet model. That's this model.h5. If you go and run some of the sample code that I have, they wanted to make sure you knew you were using the right model. So they gave me the raw model file. But if you run some of these other prediction scripts that I have, Python is able to download that model directly. You wouldn't, if you want to do image classification in Python, you don't need to have this file. You basically just include ImageNet or MobileNet and run your prediction. And we'll talk about that here in a little bit. So this is my prediction script. I'm trying to avoid showing some of the deprecated warnings since this is older code, so I have a little shell script to kick it off minus some of the warnings. Same thing with the solution. So they provide the solution template, and we'll look at that here in a second, and then we'll dig into the solution, like how did we get it to generate this example right here that we're going to end up talking about. And before we do that, code Dogger Frog. So the final solution that we'll upload to the site really looks very similar to the other two. For some reason, there's some extra noise on this sea lion picture, but in case it's not coming across real clear for you, the frog picture is even closer to the original picture, in my opinion. So let's look at their solution template. With this problem, they wanted to give you a starting point because if you're an InfoSec, a lot of InfoSec people, and really a lot of folks, period, for that matter, haven't done work in this space. I know that I wasn't really sure where to start, so I was very appreciative of any help they could provide. But a high-level view of this, um, when you're running images through ImageNet, ImageNet expects them to be 224 by 224 pixels. So we're specifying the dimensions. Next, ImageNet has a long list of known categories. In this particular case, we want to make our dog a tree frog. So we chose the index 31, which corresponds to tree frog, and then they have a human readable string tree frog, but from the model's perspective, it's more interested in that index number. And then they provided some sample code, this hash distance code, so that you could take two different images and hash them and compare them and tell you how closely they're related. Which that hash Hamming distance function is being called by this is similar image function, where you feed two different images. Basically, that's just reading the two images and then feeding the hash of each image into the hash Hamming distance, and then returning yes or no. Yes if the distance is less than or equal to 1, no if it's higher than 1. And looking at the website, I mean, some of these were off by as much as 13. And then preparing the image, this is basically reading the image in and converting it so that it's ready to be analyzed by MobileNet. And you'll have similar code examples if you're feeding images in ImageNet. And then this is a function that they provided that's just a stub that you're using to create the new image. And in this case, you're basically opening your original image and then loading the model, and then you are expected to write a solution. And then basically, if it finds an image that's close enough to a frog, like over 95% confident, and within a distance of 1 hash-wise from the original image, then it will go ahead and reshape that image and save it your file system. So we have to come up with a way to basically take our image and run it through the mobile network, and then make minor adjustments to the image and keep running it through the network until it gets closer and closer and closer to being that tree frog that we're looking for. And so this is what we had to start with. When you kick off the script, it's basically reading in Trixie.png, the original dog, and then it's writing out Trixie frog, and it's using this model. And so let's look at a solution. And I thought this solution was a little nicer than mine, so I'm sharing a solution that's publicly available. But basically, their solution starts here. And we'll go through this here in just a second, but it ends here. And everything else about this this sample code is is identical to their sample code. So I'm scrolling down to create the image, and this is going to be pretty high level. Otherwise, we'd run out of time because I know we're already at 7. But the gist of it is you're setting up your model layers. You're copying your original image to a new variable named hacked image, and then you're setting how much you want the image to change each time we loop through and make changes and reanalyze the image. And you want to keep that change amount pretty low, otherwise you're going to have an image that's way too different pretty quickly, and you'll fail because the images are just too different. And this does it. Between this and the Google article that I linked to, it does a pretty good job of explaining what's going on. So I'm not going to go through every single line, but the magic here is that they're basically saying just run this until the image is at least 99% likely to be the tree frog that we want. And so it's going to go through and it's going to make minor changes to the image, and it's going to run it back through the model, and it's going to output the likelihood that the image is a tree frog, and it'll keep doing that until it gets a 99% sure. So let's run this just to show you before we have people that need to drop off. I'm going to run this solution that we were just looking at, and it's still going to show some deprecation type warnings probably, but I tried to hide most of that so that you would be able to see what's happening here. Okay, so now it's loaded everything and it's running, and you can see the model predicted likelihood, and it's getting better and better. It's 1% sure, 87% sure, 98% sure. It regresses a little bit, 90% sure, but then boom, 99% sure that the image it generated is a tree frog. And right now it's 1904, and this image of Trixie Frog was generated in 1903. So let's look at that image again. Trixie Frog today at 7:03 p.m. and it looks just like before. It still looks like a dog, right? But let's upload that to the website and see what the website thinks of this. Before, it would kick back with detail if it wasn't similar enough. Where is this? Okay, Trixie Frog. But what we're wanting is we're wanting a flag. So if we upload this and it shows something like this, that tells us that we got the flag, and that's basically the answer that we're looking for the competition to move on. But since it doesn't show you a lot of great output, I made a prediction script that we'll look at just real quick. This is the examples like this are available publicly. The gist of it is you're defining your local image file name, and you're calling process image, which loads the image. You'll see this comment 24 by 224 by 224. It resizes the image. It converts the image to an array, and then it basically it runs it through MobileNet and gets an output. And the output is what we're going to end up taking a look at. So process, run the prediction, print the results. So let's run the prediction. Sorry, I'm going to go back into that. Which file are we looking at first? So I've got 3 files defined, but the other 2 are commented out. So we're going to run a prediction for Trixie the dog. And you can see that all of this runs pretty quickly, even on a little MacBook. So imagine how quickly people can run these type of things if they have access to any substantial machine learning hardware. So in this case, this is the same output we saw from the website. It knew that it was either 51% this dog or 48% this dog. But now if we go and we change the image to that frog that was just generated by our attack script, and we run the prediction again, hopefully it shows that it's 99% sure this is a tree frog. Okay, it's about done. And there you go. It's a tree frog, and it's 99.4% sure. Now we could go back to that attack script and change the category and run it again and have it output a different image and run it through this, and that image would then MobileNet would think that Trixie the dog was a cat or a horse or a house or whatever other category we run it through. So I'll post all of this code out on a GitHub repo and share that for anybody that wants to experiment with it. But pretty crazy that it's that easy to to fool these networks. And so this is the output that we were just seeing when we ran the attack script, or our solution to the capture the flag problem, along with the image that was generated. Comparison of the different images. These other two are scaled to where they are the same as the original one, and I mean they all basically look the same, but we just saw that MobileNet thinks that Trixie the dog is a dog, and this Trixie is a sea lion, and this one is a tree frog. So in short, if you're working with any type of models, if you're that you're training in-house and the models are critical to your business, just be aware that these type of attacks are possible. More so if people have access to your model, so keep those locked up if it's not meant for the public distribution. But if you are having to deploy your model to mobile devices or web browsers, which is a big thing now because you can basically push the processing out to the end user, just be aware that the results that you get could be could not be what you expect. So with that, I'm going to open it up to questions, and then we can either deep dive into anything after we have general questions, or just chit chat.
Jason, I have a question.
Anybody? Yeah, Chad.
So is the real vulnerability here that they're able to reverse engineer the model?
That's essentially what's happening. Okay. So the attack script is basically taking the desired input, which in our case happened to be Trixie the dog, and it's just making minor changes to the input that, as far as we're concerned, it's still Trixie the dog, or maybe an attacker, as far as they're concerned, it's still a non-fraudulent transaction, or a clean image, or whatever else it might be, and they're taking, well, I guess if it's an attacker, it would be a fraudulent transaction or a not clean image, but they're taking that and they're continuing to run it through the model and make minor changes to it to where it's still a picture of a dog, or it's still a fraudulent transaction, or it's still an inappropriate image, but they've found a way to just barely change it to where you and I can't tell a difference, but the computer is like, oh, that is a tree frog, or that is a perfectly valid transaction, not fraud at all, or that is very appropriate image. So that. You're absolutely right. I mean, they're essentially reverse engineering the model, but it's more of a brute force of the model. That might be a better description.
Okay. Yeah, so
they're not tearing the
right. So
they're not tearing the model apart. They're basically just trying combinations until they find something that gives them the answer they want.
So if your model sits behind an API or something, someone's going to really have to hammer that API before they can generate one of these.
Yeah, they're going to get cut off by rate limiting or security checks or something like that, which is why I suggested the idea of hosting that model and sending a request, or exactly what you just said, basically hosting it as an API, and the end user sends a request and gets an answer, so that they can't sit there and just hammer away at it. Because in the time that I was sitting there waiting for an answer, I mean, my computer could have just sat there and run thousands and thousands of attempts without anybody being the wiser, because the model is local. Good question.
So in the example of a bank, and you had said a $6 check getting turned into a $6,000 check, or so what are they actually using besides secrecy and actually not hosting the code on the individual device?
I'm sorry, say that very last part again. What are they using? What?
So how are they guarding against that? I know that you had mentioned secrecy of the exact code, but also They're not putting it on your individual mobile phone.
Right. Okay. So how are they protecting against this? Certainly keeping the model secret and not deploying it out to the edge devices, the end user devices. But if you absolutely have to deploy out to end user devices, just because it's very lucrative to do that, a majority of your cost in a model is is calculating the output. So certainly there's a cost in calculating or in building the initial model, but once it's deployed, if you're doing something like Chad suggested, where you're hosting it behind an API to protect it, you're having to pay for every single one of those predictions because you're either having to pay for the compute power or what have you. Whereas if you deploy a model like MobileNet, the one that we've been talking about tonight, it's designed to be deployed to an end user device, and the benefit of that is twofold. Number one, the operator isn't incurring the expense of the predictions because that computation is happening on the mobile device or the browser. But number two, and more importantly for a lot of people, is that those predictions can happen offline. So all of the sudden, if you have some sort of app that doesn't necessarily need to be web connected all of the time, or maybe is behind some sort of high latency internet connection or low speed internet connection, they can be performing predictions on an end user device and not having to send round trips out to an API and back. Specific example being, I want to say there's a Google type app that you can point at foreign languages and it'll basically take a picture and then translate the language to English. That can happen without a round trip to the internet, from what I understand. But just so you understand why you would deploy just out to the edge, if you're doing that, the protection against bad data coming back from the edge would either be manual review of data. So I gave the example of a bank with mobile deposit, at least the bank we work with, the branch that the mobile deposit comes into, like let's say it's a bank with 100 branches. I know that my branch manager has somebody at their branch that's responsible for reviewing the mobile deposits for their customers. And they basically make sure that the amounts are correct, because then they have that personal relationship where if there's an issue, they can reach out to the customer and resolve any issues. But that type of manual check or individual check isn't always going to be feasible. So what you could also do is have some preliminary model or filter out at the end user device, and maybe something more sophisticated server side, so that when something does come back, it runs through a secondary check, or at least some sort of range of parameters. Like I gave the example of a website where somebody is presented with a list of customers that they want to view. But let's say you're using some sort of mobile audio model where they can say, I want to see the record for this person. And then that's transcribed to some sort of name. You'd want your server to still check that name and make sure that name is somebody they have access to look at. I mean, that's a simplistic example, but the moral of the story is if you're deploying these models to the public, you just need to be sure you're not trusting whatever output comes out of them, because the public could deceive you.
Well, Jason, I think the key point you made earlier was that it's critical to your business, right? If you're just detecting cats or not
Right.
cat, that's probably not critical to your
probably
business.
Okay if it's not a cat.
Right. So if it's for entertainment purposes and it's at the edge, no big deal. But if it's transactional with, potentially disastrous, outcomes or something, then it makes sense. Have you heard of anybody solving this with like ensembling or anything like that?
So there is work to basically protect against what they call adversarial examples. That's still still pretty young, but as that progresses, I'd love to share some info there. But no, there's not substantial enough progress to really share at this point.
Gotcha.
Yeah, good question though. At least none that I've seen. If anybody's seen differently, please share. But if you do think of other questions after the fact, feel free to hit me up on Slack. I'm not online 24/7, but I try to check for notifications every day or two. So if you ping me tonight, I'll probably reply right away. Otherwise, I'll try to get back with you ASAP if you send me anything. I mentioned that I'll share the slides and code samples out online. The slides have links throughout the slides with little footnotes, but I also have some references here to like the Pico CTF challenge and then the solution that I demonstrated tonight. With that, if there aren't any other questions, just thank you to everybody for coming out tonight. And if you want to stick around, I'm glad to chit chat for a little while.